Hello and welcome back to the lab. Today on the bench we have the continuation of the... I've been staring at this for long enough, you'd think I know what it is at this point. 8165. We're going to start, I have the control panel out again. We're going to start with replacing this spring. I completely forgot that the lab has a source of West key switch parts. So didn't need to cut it, didn't need to order the shims. Oh well, sometimes that stuff happens. But we know we can cut shims if we need to, which is good. And I'll show you guys the cutter that I used for that. It is a, it's substantial. One of the other uses that it gets a lot of in the lab is actually cutting PCBs. So whenever I make a custom PCB for something, things like that, it's how I cut out the FR4. We're going to go get a spring, and I'll show you how to put one of those in. Okay, here we have the key panel for a 3325A that was absolutely terminal. The power supply went south in it and just cascade failured a whole bunch of the boards and very rapidly went to beyond economic repair, so we'll use it for parts. Oh, I already shot the piece that I need out. This is a little piece of spring steel. It is 0.05 millimeters thick, so very, very thin. Here's the one we made in the lab. Come on. There it goes. Which is 0.1 millimeters thick, so it worked. It was just a very, very stout button. I didn't want it chewing up the plastic because there's a little notch on the key itself where the spring steel tab comes in, and then there's a little notch down here where the tab rests in. So when you press a key, that's it. That's all it moves. So it pushes down, which causes this to pop out, but then the spring tension pushes the key back up. So I did not want too heavy of a spring just chewing up the plastic because that wouldn't withstand the test of time. And one of the things we like doing here in the lab is getting this stuff ready for the long haul. Let's put one of these in. This goes in. That capacitor is going to be in my way again. Most of these are pretty easy, but this one's going to argue. There it goes. Now we need something to direct it up a bit because it's already caught, which we don't want. This is much easier not doing this around the camera, but we do what we got to do sometimes. Get a screwdriver in there, just pop the leaf up just a little bit. Get my flat blade. That worked a little better last time than the pliers. Push it up with a flat blade. And there, it's in. Get it straightened out. That's way out of the notch. Okay, just had to line it up side to side and then push down a little bit on the top, and functioning key spring, and it feels like the rest of the buttons. So that's now ready to go. We can throw that back in the 8165. Okay, I got the two capacitors out that I wanted to replace. This one with the way the shrink tube marking was looking, I wasn't too thrilled with that, and when I pulled it out, I did see a bit of corrosion coming out of the cap on this side. If we test it, this is a 220, 287, that's a little high, so it is starting to dry out. This one is a 65. 78, so it was starting to show a little age too. So There is a lot of hermetically sealed tantalum capacitors in here that are in glass cases. They are extremely high quality and typically do not need to be replaced. Also, these huge electrolytics back here typically do not have a problem, and they can stay in circuit as well. If they do have a problem down the road, they're very easy to change out. They're just screw terminals on the bottom of the board. You unscrew the cap, you pop it out, put a new one in. These are also, if you wanted to replace these, they can be horrifically expensive. This cap could be $100, depending on the size and voltage. So those are replace as proven bad, but they typically do not go bad very often. So I'm confident leaving them in there. This unit's also destined to stay in the lab with me, so if it shows up on the bench again for another video, you guys will know I was wrong. This is normal because we have no batteries. And I think I've decided to ultimately not replace the batteries in here, so I'll have to set up the parameters that I want every time I turn it on. Not necessarily a bad thing. It'll also save me the problem of corrosion down the road. I don't know quite yet how much use this is going to get on the bench. I have several other signal sources and function generators and things like that that are available to me. So we'll see how often this gets pushed into service. One of the reasons I'm keeping this around, though, is the 50 megahertz. This is quite fast for a synthesized unit like this, which is why I was interested in grabbing it. The other ones that I have, the 3325s, they only go up to 25 megahertz. And then they have different limitations depending on what waveform. I believe this does, well, let's see if it yells at me. Square wave, duty cycle 50%, frequency 50 megahertz. Yeah, it'll do 50 megahertz square waves out of this one. So quite quick, and even though it's a very vintage and older unit, still highly useful today if you have the physical space for it. This thing dwarfs my Rigol function generators. This is huge compared to some of the more modern stuff, but definitely still very viable. All right, well, 50 megahertz square waves. Actually, the clock is incredible on this still. It doesn't even need alignment. What is its frequency? How good is it? Well, that's not too bad. Gate time. We'll do a 5-second gate time, take a good look, let it count some more. Well, that's not too bad considering that the frequency counter's not warmed up. I just powered it on, so it's going to drift up a little bit, and it's going to get even closer to 50 megahertz. So I'm not unhappy with that at all. Well, we'll throw it on the scope, let it run for a couple of hours, get nice and hot, make sure we don't have any other problems where anything's going to burn down. And then we'll probably line up the output section, but I don't know if we're going to get much better on the time base. I do plan on putting this on the rubidium. So that's going to be coming. I got to get the rubidium source over to the other rack. That's going to be part of the problem. So I have a lot of labs kind of split. I have the tech side. I have the tech side over there. I have the HP side over there. And I have a lot of 10 megahertz stuff, reference stuff on the left side of the lab, but the rubidium's on the right side of the lab. So we're going to have to work on getting the 10 megahertz over there and distributed, but we have some really cool future plans, and that's it's going to be a little bit of foreshadowing as to what might be going on behind the scenes. All right, we're set up for starting the alignment of the output stage of this 8165. We've got a 1-to-1 probe hooked into TP3 on the A4 board. The A4 board is the bottom board of the power supply. And we're adjusting this for minimum amplitude coming out of the unit. And minimum amplitude looks to be about 2.3 millivolts on this one. Here's what the scope looks like. It's so low, scope's having a little bit of trouble triggering, which isn't too bad. from the schematic TP3, and then the adjustment is actually below the fan in the back of the unit, so the fan sits about right here, and then this is our adjustment resistor that we're tweaking. All right, we need to check invert, and that's fine. Invert wanted to be less than 10 millivolts peak to peak. Well, our test point 2 is off. Test point 2 was actually quite hard to find. Test point 2 is hiding underneath these two resistors here, and I'm picking up ground off the case. All right, looks like we have some troubleshooting to do. Test point 1 is located right here, and that is the negative 4 volt adjust. So where that's coming out of is this is the D to A converter. So it's coming right out of here, and it's hitting this test point, and this test point feeds the positive input of U802, both op amps in U802. Other than that, it doesn't go anywhere. We'll zoom into the schematic here in a second, but so there's very little current running through here, but adjusting R805 isn't doing anything. So, and this portion of the circuit is essentially where it goes back from digital to analog. So this is definitely probably some of our offset. Here's our schematic we can take a look at. Here's our D to A converter, and here's 805. So this is our resistor that we're adjusting. And all this does is the output 0 to 2 milliamps, so it's current driven D to A, goes through this 194K resistor, has this which adjusts to ground, and then it drives these two op amps, and that's it. That's all it goes. Test point 1 is right here. So there's no reason why this should be just railed at 6.9 volts when we want 4, unless drive is bad. So I'm looking at this D to A converter. I really hope it's not this chip, but there's a zener diode in between two resistors for the reference. We have a negative reference and a positive reference for this IC. So if the reference isn't working correctly, because D to A converters are very susceptible to reference problems, or they react poorly to unstable references, let's put it that way. If there's anything wrong with this zener diode and it's not setting up the reference correctly, that's going to peg the output of the D to A and cause some problems. So before I blame this D to A, which I'm really hoping isn't, because I have control, like I can move voltages and things like that, they're just off, it's offset. So it's not zeroing correctly. So I don't think it's this chip, because this is one of our main driver chips, and if this was out to lunch, we wouldn't have near as much control on the front panel as we would otherwise. I do want to check this zener diode and see what that looks like. So let me fire up the curve tracer. We'll throw that zener diode on the curve tracer, and we'll take a look. All right, let's go to the curve tracer. So I have it set up in AC mode, 25 volts, and 0.1 milliamps vertical. Voltage on the horizontal, we have 2 volts of division. So what we're going to do is we're just going to start giving it some power. Let's see what this zener diode looks like. That's going to be 2, 4. Okay, this looks bad already because we're not getting any V forward. For a good zener diode, we should be getting V forward at about 0.6, and then we should be getting a zener voltage when we hit the zener reference, but I don't have a V forward yet. 6, 8, up. It's starting to dip. So right here, it's starting to dive down. So we do have zener around 8-ish volts, but no V forward. So I think our zener diode, which is setting up our reference for our D to A, is a little bit toast. Let me have a look around the lab and see what I got for zeners. Well, I was going through warm-up again because things make a bit more sense now. And why would they? I don't understand why we would do this, but let me show you guys what's going on. So I grabbed the wrong test point. Test point 1 is actually right here. That is test point, oh, you can't see. This is test point 2. That is test point 1. The other thing to note is, when you do this adjustment, the unit has to be output off. The service manual actually doesn't say that. So there's our negative 4 volts. If I turn the output on, or, I'm sorry, the output has to be on. If I disable the output, we get nothing. If I enable the output, it's on. So I had the front panel in the wrong place, and that's why it was confusing. What is confusing about the front panel is lit up is disabled, off is enabled. Because that makes sense. But once we have the output enabled correctly, it's an easy matter to adjust the 10-turn pot. Even with a 10-turn pot, this is touchy. Because they want 4 volts plus and minus 3 millivolts. And there's our offset problem. So this is the op-amp balance for U3, and this is supposed to be 0 volts plus and minus 0.1 millivolt. And we're off by negative 33 volts, or negative 33 millivolts. So that is very similar to what my offset was on when I looked at it at the scope. So very likely this is going to fix our problem. And to adjust, it is this potentiometer right here. That is R20 on the A12 board. Yes, it is. Well, that's not doing anything. That's because I am again on the wrong test point. So many of them in this unit. There's our balance point for U3, so that looks good now. I grabbed test point 6 instead of test point 1. And U4's balance was off a little bit, not too terribly. That's not bad. Okay, to check the amplifier balance, we're going to let the meter do some fancy settings. I bumped up the power line cycles to 10, and I turned the filter on. We're also going to turn on the relative measurement. And now when I hit the invert button, the measurement needs to be relative 5 millivolts or less to the positive direction. So we hit invert real quick. Going to give the meter some time to settle. And so we are within 5 millivolts of the, actually we're within 3 millivolts of the relative measurement. So that one passes. Well, I am staring up from the bottom of the rabbit hole, and man, is this one deep. We've got, but I think we've made some progress, and we will get into this while I wait for this thing to warm up. It's been off too long for me to align. All right, first things first, let's see if our offset voltage has changed. I've been arguing with this offset voltage for about 4 hours at this point, trying to understand a schematic that is very broken and a bunch of things moving around, which I will explain. Fire up the unit, and we're going to frequency 110 hertz, triangle wave, 50% duty cycle, no modulation. We're going to offset to 0. We're going to amplitude to 1, not 199 volts, that's not going to work. 1.99 volts. Going to enable the output, and we now have a positive output voltage, or offset voltage, which is good. That means we have changed it. Let's do a preliminary real quick and see if it will actually align, because we've moved it about a volt in the opposite direction. Oh, it's going down. Let's see if I have enough adjustment. If I have enough adjustment, that will be absolutely fantastic. It's a 17-turn pot. It's a race to 0 or the bottom of the potentiometer, and I'm not sure which one's going to win. Well, it adjusts. Now, we need to let it warm up, make sure it will stay adjusted. But it does 0. All right, it took me forever to find these adjustment resistors in the schematic. This is a really weird and kind of broken. R1 and R2, which are the two offset adjustment resistors, are right here. They're 20 ohm, 17 turn potentiometers, and essentially they're feeding this op amp U202 with the bias for the offset. What was happening is my 1X amplifier, it was pegged, so I didn't have any more adjustment, and I still had a negative 400-ish volt, 400 millivolt offset, and it wasn't coming out. So it took way more than I'd like to admit to find this section of the schematic, but we have an op amp with a little bit of bias. We have a zener diode and a resistor biasing the positive side of the op amp, and we have some resistor networks and these adjustment pots biasing the negative side. Output of the op amp drives these two transistors, which then feed back on both sides, and it appears from the schematic both of these use the negative 20 volt rail. This cutout here is because these two resistors are on the A6 riser board. This circuitry is on the A4 power amp, which is the board that's flat. So we got the adjustments up here, and the actual circuits are down here. So tracking some of this down got interesting. Also, a couple of these resistors are on the far side of the socket, and a couple of them are on the visible side of the socket. The board's in the way. Actually, R217 is on the far side of the board. But I was going through everything, and I was checking all these resistors, and I was checking it because I had a negative bias problem. I was checking everything on the negative side. Maybe I wasn't getting enough bias or anything like that, and then everything was checking okay. All these resistors were testing good. These transistors were testing good. Everything was testing good, so couldn't figure out what was going on. Op amp was obviously working. We knew the op amp was working because I could adjust it. If I adjusted the potentiometers, stuff would move. It would just not move in the way I needed to. I could go from -6 to -1.3 by adjusting this potentiometer. So I had control, and the circuit was working. I just didn't have enough adjustment. I checked these two parts, this resistor and this zener diode, on the positive side, because if I didn't have enough adjustment, I'd also looked at this potentiometer, and it was fully bottomed out, asking for more and more and more and more and more negative feedback, or negative input. So I was like, well, maybe I'm getting too much on the positive side. And so I checked this zener diode, and I checked this resistor. The resistor was fine. Actually, here's the resistor itself. I pulled it out, and that was totally okay. Zener diode, however, instead of being a 5.1 volt zener diode, it was testing at 4.8 volts. I was not getting enough drop off the zener diode, which was biasing up the positive side of the op amp, which meant I needed more negative to bring it back into balance, and I was out of negative. It wouldn't work. So what I did, because I looked for I looked to order some zener diodes. I still have the 9 volts, but that ended up not being what was faulted out. I looked for a 5.1 volt zener diode that I could order, and I couldn't find any that wasn't surface mount, things like that. Nothing in through hole. So the way I could get around this and to get the bias string, I upped this resistor. So I still have the zener diode in here that's drifted slightly with age, but I gave it more resistance. I took this from a 156 k ohm resistor to a 220 k ohm resistor. I was shooting for 200, but I didn't have any 200s in the lab, so 220 was the closest thing I could try here. This was good news, however, because as we saw previous, it gave me enough adjustments. So I just need to wait for this to warm up again, and then I can adjust the bias set point, and then we should be good to go. All right, with the new resistor in and a slight readjustment of the potentiometer, the offset is gone. So we are looking really, really good. The resistors in question look quite different. Let's zoom in on that. So here's what we had in the unit before, just a standard, decent sized 2200K resistor. This is the new Precision 200K resistor that we got to put in it. Part number is right there for anybody following along at home. And you'll notice it's a 0.1% 1 watt 5 ppm resistor. So this is quite the exotic resistor. The 5 ppm temperature coefficient is what stabilized it. This resistor was not very stable once it warmed up, and it was jumping around a whole bunch. The DC offset was not stable, it was wobbling around. And that was just due to this being a cheap resistor. This is, you can get 100 of these for $2. This was a $17 resistor. So it was just needed to buy a better part. The reason I went the resistor route as opposed to the diode route to fix this particular problem is realistically the diode should be replaced. This is a unit that's going to stay here in the lab, so I don't need to worry about it too much. If it ever goes out again, I can fix it. But the diodes were back ordered for 52 weeks. So I wanted to get this unit up and running, knowing it has a little bit of wobble on the DC offset, but it's fine for my needs for what I'm doing here. So this will be a fine repair for now. If it becomes a problem in the future or I need the accuracy for some reason, I can always order up a diode, wait a year, and get a diode put in. The diode, the 5.1 volt zeners were available. The big problem was the temperature compensated ones. The temperature compensated diodes were on the 52-week back order, and I wasn't able to find them readily. I did get the 9 volt temperature compensated diodes, and those were not inexpensive either, but they weren't as bad. Or the 5 volts were about the same price. Quite a bit for the TC diodes over the standard zeners, but it's a precision part, so it comes with a precision price tag. So this unit is now ready for service. It's going to find a home on the bench right over there, and it's ready to rock and roll. Thanks for stopping by the lab and taking a look at the part 2 of this 8165A repair / restoration, I guess. Looking forward to putting this to use in the lab in future videos. Take a look at the Patreon page if you would like some more content. Patreons are running ahead. They have early access to all the videos that end up on YouTube. There is currently nothing behind the paywall, at least at the recording of this video, but those that do support the channel have early access to a number of videos. The patrons' support to this channel greatly helps keep the lights on in the lab. Their support cannot be understated, and I am eternally grateful for all the support that everybody's shown me on the channel and everything moving forward. As always, more videos are on the way. Hit me up in the description between videos. Comment section between videos. I read all the comments on all the videos, and comments can spawn videos. So if you have questions, comments, concerns, let me know. We'll see what we can get recorded. With that, I will see everybody in the next video. Bye for now.